So, Honorable Minister, Mr. Ambassador, ladies and gentlemen, it's an honor to be here and be able to present our work on indoor positioning, and in particular, the tagline for today's presentation is efficient movement of people, and I will come back to that later on. But in particular, I will present our activities within a project that was within the Vinnova DST Indo-Swedish program on embedded system. The title of the project is quite long, and I will not penetrate it in detail, but this is a 3-year project that we have just started, and we see a picture here from our first internal project workshop at the Indian Institute of Science in Bangalore. We also have a special stand here in the control room where we have some more details about the project, and also a direct link with our Indian principal investigator, Professor Hari. The project is about what we call a personal navigation system, here illustrated by a set of firefighters during an operation. In the military context, it's often called blue force tracking, and it's the purpose of the system is to give information about the position. It can be the absolute position, for example, useful for the command and control officer who like to know where the position of the operators and like to put it on a map. Or it can be the relative position within a group of operators. They like to know if the colleagues are to the left, to the right, behind, and so on. This has been identified as a needed tool for increasing the safety in different kind of professional rescue operations and similar operations. And there has been a lot of international initiatives, for example, the Glancer program initiated by the Department of Homeland Security in the US, or the WARE-2 consortium within the 7th European framework. And also, of course, there's a lot of military activities in this kind of area. To try to summarize the technical specifications, we need typically an accuracy in the range of a couple of meters, 1 to 3 meters. It is a system that should be work from high floors down to possibly many levels underground. And it's a system where in this case, the firefighters, they have to bring their own equipment. We cannot rely on any available infrastructure, so we have to bring everything we need in order to solve the task. The main challenges, first of all, the first main challenge is to get accurate position. Not only the position, but also orientation, maybe the direction and velocity of the object. And we cannot rely on for example, on the satellite navigation system. So we can conclude that GPS or other satellite navigation system, they are not enough. The second challenge is the wireless communication. We need to have a robust wireless communication, and we cannot rely on the available infrastructure like the mobile networks. The approach taken is sometimes called robust multi-sensor positioning, where as I said, we bring all our equipment, we bring the sensors. We typically put the sensors on in this case, the firefighter, GPS antenna on the helmet, maybe a camera on the shoulder, some measurement units on the back, and maybe some inertial measurement unit measuring acceleration and rotations on the boot. What also is considered in this kind of problem is that we, of course, in order to increase the performance, we should use the position information in order to improve the wireless communication, and we should use the wireless communication signals in order to improve the performance of the positioning. This is an example we have on the left-hand side. This is inertial navigation sensor measuring the acceleration and rotations, and then using classical mechanics we can calculate the position. And on the right-hand side we have a system with a radio ranging equipment, And we can see this equipment on display later on. If we use them standalone, we have on the left-hand side, we see the effect of using a radio positioning system. The red lines are the ground truth or the trajectory of the object, and the blue lines are our obtained position estimates. On the right-hand side, we see the same results with using the inertial measurement system. And if we do combine them in a wise manner, we can get an improved performance. Our approach to attack the problem is we approach it on all fronts. We have a solid research program in basic research where we try to solve the fundamental questions, and we present results in the scientific journals and conferences. We also build the prototype systems, here illustrated by our radio ranging system and the sensor mounted on a boot. And doing these prototypes, we get some feedback to the basic research program, so we are able not only to solve the interesting problem, but also the relevant problems. Of course, we also like to combine all the modules or the different I sometimes call them intelligent sensors into a full system. And if we have a full system, we also need a place or site for the evaluation of a full indoor positioning system. And that's the reason why we are here today, because I think this is a fantastic site for these kinds of experiments. And the reason there are many reasons for that. First of all, it's a full scale size, and it's three-dimensional. Not only the horizontal position is of importance, but also importance is the vertical position. And here we are actually having 4 stories of office space that we can use for that kind of experiment. Since we are 20 meters below the ground, there will be no interference from the wireless networks or other radiation sources. Also, that is maybe more important, since this is an isolated area, we can use it and we can create our own radio frequency surroundings. We can simulate that we are doing positioning in, for example, a burning industry or something like that. Another important feature is that even though we are underground, we have a direct indoor-outdoor access via an escape staircase. So we can also test systems that when we like to test the transition from outdoor coverage to indoor coverage. And since this site has this nice feature, we have just recently installed a reference system so that we in a larger scale can have a reference ground truth when we evaluate our own systems. We also think it's a very good site for attracting the end user. It's easy to get there in the downtown Stockholm. And what do we like to do here? Well, we like to evaluate our own 8 user systems that we are developing within the Indo-Swedish project. In 2013, we will have 8 user systems here at KTH and also 8 user system at IISc in Bangalore. Maybe we can test all 16 units at once, hopefully. We will also use this site in order to develop test methodologies. It's not clear today how you should evaluate the system, how you should test the system, what are the relevant figure of merit, and what are the figure of merits for different kinds of users. And we also like to organize benchmark tests. This activity is also an action within the ECT labs that Drayev mentioned. I have 2 more slides just to put this technology in some kind of context, or starting with in-car based navigation. That is today a mature technology. We have the tools in the cars so that helps us get from point A to point B. We have also during recent year seen similar functionality in our smartphones. We can now also use it for pedestrian navigation. If we see to the underlying technology, the in-car based systems are typically multi-sensor based, so we are not only relying on the GPS, but also using additional sensors in order to improve the performance, such as accelerometers, the information about the speed of the car, map information, and so on. The smartphones, they are on the other hand connected to the surroundings, so they use assistance from the mobile networks, so they use something called assisted GPS. We are now, in the future, would like to see these professional systems as an embedded system. I can imagine it will be a similar size as a modern mobile phone, but we have a more stringent requirements on the performance. Another clear trend is to use these kind of sensor systems for improving traffic flow, not only for take you from point A to point B, but also take you from point A to point B with your car in an intelligent manner. And we also have a clear trend with system for indoor navigation, typically in large shopping malls, where you like to have your personal shopper in your mobile phone, taking you from from the first shop to the next one in an efficient manner. These are they have a lot of similarities, these systems, but they have a main difference, and that is the use of the infrastructure. From our system that has a requirement that we cannot use any infrastructure, to the shopping mall where we can have a full use of the infrastructure. We can add electronic tags outside the shops and so on. So if we go for what will happen in the future, of course, with this technology, we can see that we can not only have isolated groups, we can use it for applications for where we have large crowds, efficient navigation and positioning in a large crowd, how to find your family members when they are lost. We can use it for traffic flow, both for prediction and also to try to improve the traffic situation. And we can also have it for improved navigation in terms, not only take you from address A to address B, but also take you the full way to the person you like to meet in an office space in a large building complex. Thank you. It's all about efficient movement of people. Some acknowledgements. The plan now, we will have some refreshments, and then we have 4 stations here where we present a little bit more in detail our activities within the Indo-Swedish project. We have 2 stations showing our what I call intelligent sensor. We have 1 station that shows the reference system and its performance. And finally, we have a station where we have a short description of the Indo-Swedish project and also a direct link with the Indian investigator. Thank you.